Here we go, question 12 of 0654, Winter 2017, paper 4-1. Okay, now we've got a swimmer in a swimming pool, we've got a driving force and a frictional force. A frictional force probably water resistance more than anything. And we're being asked to state the size and the direction of the resultant force. Now this is, I think, probably a slightly nasty question because resultant isn't a term that we use very often in GCSE level physics, and basically it means the total. Now, if you've got two forces, your initial temptation would be to add these things together, but remember they have direction and therefore they are vectors. In this sense, we need to think about the direction when we're adding them together. This force is to the right, this force is to the left. Well, we should be aware that if, for example, we had 100 newtons to the right and 100 newtons to the left, then the total force here would be 0. We'd be balanced. We're not quite balanced here, we're unbalanced. We have a force of 100 to 80. Well, 100 take away 80 is 20 newtons, and that 20 newtons goes to the right. You could also write forwards here, or in the direction of motion. Now, we're then asked to state how the speed is changed, and then explain. So 1 mark for the statement and 1 mark for the explanation. Key point here is to think about our idea of the equation we've used in the previous question, F equals to ma. And this, I don't know, I'm not sure if this is one that we appreciate quite strongly enough. This is a huge equation in physics. It tells us what happens in systems where a force is acting. This F really means the resultant force. The resultant force is the total of all the forces acting on a body. If we have a resultant force acting on a mass, we will have acceleration. This means that the force is unbalanced, and therefore our body changes its motion. So in this case, the speed will increase because there is an unbalanced force acting on the direction of the travel, in the direction of the traveler. Now, what we could say, we could pose another situation where these forces were flipped, where my frictional force became 100 and my driving became 80, maybe later in the swim when he's more tired. Well, in that case, our frictional force would be greater than our driving force. Again, we'd have an unbalanced force, the difference being that the speed would decrease because there's an unbalanced force acting in the opposite direction of travel. In this case, however, we're driving forward. So this F is really important to bear in mind. F is the resultant force. Okay, the swimmer starts the race when he hears the starting sound. I'm really hoping this picture is becoming familiar as well. It's coming up again and again and again. We've got a sound wave here, C and R. C stands for compression, R stands for rarefaction, not refraction. Okay. Now, we've got a figure here, and this figure is really what we're looking to sort of explain or describe the difference between region of compression and region of rarefaction. Well, you can see here that these lines, again, I like to think of the accordion, okay, these lines are where our particles have been close together, pushed close together, and these sort of less dense spaces of lines are where we've got particles further apart. And the result of this is that the compressions are areas of high pressure, and that's because of the close proximity. I've used the word close proximity, I could say low interparticle distance, okay, whereas rarefactions are low pressure because there's greater separation. Okay, so really these lines are trying to represent our the spacing between the particles, or the positions of the particles. And a small point I just want you to highlight here, if I just draw two points here, I want to draw our usual waveform. Now you should be aware that waves tend to look not like a bunch of lines, but like something like that. Okay, and if I continued it the other way, just so that we kind of, oops, that's a terrible drawing. Okay, we're starting to look something a bit more familiar to our wave shape, right? Remember, whenever we draw a wave, we represent it in this kind of sinusoidal form. Well, if you notice there, I've got a compression to a compression. That is one complete wave, and so the distance there is one wavelength. Okay, be aware that we're representing the wave in different ways here. Okay, we've had exactly the same question in another paper, and I've tried to do it another way. Water waves are transverse, sound waves are longitudinal. Describe the difference between a transverse and a longitudinal wave. Okay, key point here being the idea of direction of motion and direction of the wave and direction of the oscillation. In a transverse wave like water, we know that the water goes up and down, but the wave moves left and right. In a longitudinal wave, we have, for example, sound, the particles moving backwards and forwards, and the wave also kind of moving in that forwards direction, for example. And that's what I've tried to draw here. Particles moving up and down for transverse, but that oscillation moving to the right. So we would have a particle here moving up and down, and then at some time later a particle here moving up and down, and a particle here moving up and down at some time later. So this is the oscillation as it spreads through. In this case, we would have it the other way around. My particle here would move to the left and right. At some time later, this particle would start to move left and right, and then this particle would move left and right. The oscillation is spreading in the direction of the travel. Okay, and that's what I've written here. Transverse waves, the oscillation is at right angles to the wave direction, whereas in longitudinal waves, the oscillation is parallel or in the same direction. Okay. Last one, and I think this is the one that is going to trip people up. Okay. This is a hard question. This is all about what kind of happens when when light comes out of water. We've got two rays, and you're being expected to draw what happens to them as they reach the surface. Okay, you don't have to think about what happens after. Just you don't have to think about any later points. Okay, we could talk about this over here. You just need to think about what happens when they meet these. Let's take X. Okay, we've got light traveling from a dense medium, so a slow medium, to a fast medium, air. Okay, remember air or a vacuum is the fastest one that we can go through. Well, I think it's probably worthwhile to think about our original kind of picture that we have of light coming in. Yeah, it's a very small drawing that I've done here. This should be hopefully familiar to you. We had this idea where we went from air into glass. Yeah, A, G, A again. Yeah. When air goes into glass, it bends towards the normal. When it comes from glass to air, it bends away. So from fast to slow to fast. Here, we've very much got this situation. We're going to bend away from the normal. So you can basically draw anything, yeah, that is allowing that wave to bend away from the normal. Hopefully that's clear. You're going from a slow to a fast. If we were going from fast to slow, it would bend towards the normal. You could also draw a wave coming down here, because we know also when we get when we have refraction, we also may have a little bit of reflection as well. Okay, but not a lot of it. The difficult bit is where we get to here, because we've been told in the question something called the critical angle, 48 degrees, and this number here is very much greater than 48 degrees. Now, what does that mean? This means that when we strike the water at this angle, then the whole wave will be reflected. So what we're expecting is a line to be drawn diagonally down to the right here, and obviously if you were drawing this with a protractor, it should be 60 degrees as well. That's because total internal reflection has happened. Okay, so we've got an angle of incidence, yeah, and we've got the critical angle. Yeah, if the angle is less than the critical angle, then we will get refraction. Okay, if the angle is equal to the critical angle, what will happen is the angle of refraction will be 90 degrees. So that if this increases to 90 degrees, basically going along that surface, that would be my line for if it was equal to the critical angle. However, if I is greater than C, then what we get is total internal reflection, TIR. So the way I've explained this At x, the angle of incidence is less than the critical angle. Yeah. So the ray is refracted away from the normal because it enters a faster medium. That's probably a bit too much information, but I think I'd definitely get the marks for this. At y, the angle is greater than the critical angle, and so total internal reflection occurs. Okay, that's a hard question, a lot of possibilities there, but we're trying to dig out these questions as early as we possibly can, so that we can then not be shocked when we meet them in the exam.